Hello and welcome to Engineering Economy. This is Dr. Ola Kamerdiner. We will talk today about difficulties in solving for an interest rate. That is an additional material for Lecture 7. Here's our outline for today. We will discuss why multiple solutions can occur. We will discuss modified internal rate of return or MIRR calculation. And we will talk about solving MIRR using spreadsheets. Specifically, our learning objectives for today is to understand why multiple solutions can occur, to be able to identify when multiple routes can occur, and we will also develop and use spreadsheet in solving MIRR. Let's take a look at this example. This is an example for additional material for Lecture 7 or Chapter 7, and it shows the example of cash flows with multiple solutions. In fact, here's our years, here's representative cash flows. So notice, right, we have positive cash flows in years 0 and 1. Then we have 2 negative cash flows in years 2 and 3. And then we have 2 positive cash flows in years 4 and 5. If we drew a cash flow diagram, it would look like this. In fact, 2 positive cash flows, 19 and 10 respectively for 0 and 1. And then for 2 and 3 we have 2 negative cash flows, arrows pointing down. The same size errors because it's 50 cash flow in both cases. And then we have 2 errors pointing up for 2 positive cash flows of 20 and 60 in years 4 and 5. If we were to find a present worth of all of these cash flows for different interest rates, starting with 0 all the way through 50, and then plotted them as a plot of present worth based on different interest rates, we would obtain these function. So you can see that this is the present worth function as a function of different interest rates. So you can see what's interesting about this function is that it crosses this net present worth level of 0 or level of 0 net present worth twice, slightly after 10% and then slightly before, a little bit before 50%. So this is very, very important to notice that there could be cash flows that will give us multiple solutions, right? Based on our definition of internal rate of return, both of these values, this I that corresponds to this crossing of 0 level present worth, and this one would be the internal interest rate. So the question is, what is it? Which solution should we select? Because of course, there's only a single value of interest rate. So why multiple solutions can occur? More than one sign change in the cash flows. And so notice, right, that's exactly what we had here in these cash flows. First we had the sign of positive cash flow, then we have negative. So that's one change from positive to negative, and then from negative it changed to positive. So it's a second sign change. So in fact, if we have more than one sign change in the cash flows, we could have multiple solutions. So notice we would set present worth to 0, and this would be our equation. Of course, that's a very general equation for n periods with different values of cash flows denoted by CF. I is representative, or not I's, but say M's, where M represents a specific year. Because you can't really use I already denotes interest rate. So you can see that CF0 is cash flow times 0, CF1 cash flow times 1, CF2 is cash flow times 2, and CFN is cash flow at the end of the useful life of the project. So now, if you look at this, when we have this type of, we need to find I from this type of equation. When we have different multiple signs change, or more than one sign change in cash flows, this equation is likely to produce multiple solutions. So if we set 1 plus I to the negative 1, or 1 over 1 plus I to be denoted by x, then this will look like this. And so, in fact, if we have multiple changes of signs in this type of equation, we are we're going to expect to get multiple solutions. And that's based on Descartes' rule. If a polynomial with real coefficients has m sign changes, the number of positive roots will be m minus 2k, where k is an integer between 0 and m over 2. Again, very important, it's a mathematical rule that guides these polynomial equations. So if a polynomial with real coefficients, and of course cash flows are going to be real coefficients, they're either positive or negative, they're real coefficients, has m sign changes, where m is more than 1, then the number of positive roots will be m minus 2k, where k is an integer between 0 and m over 2. Notice that if we had m equals 1 in this case, then it would be 1 minus 0, because k is an integer between 0 and 1 over 2, so the only integer available is 0. So we would have a single positive root when there's only one single sign change. But for multiple sign changes, we could have multiple number of roots. Of course, why we have positive, why we keep in mind that it's positive, because interest rate is always positive. Number of sign changes. For 0, as you can see, if you plug the 0 in, we would get 0. For 1, it would be either 1 or 0, number of positive values. For 2, we could have 2 or 0 number of positive values of x, and therefore we would have either 2, 1, or 0 as number of positive values of I. And then for 3, we can have 3 or 1. And we could have 3, 2, 1, or 0 as a number of positive values of I. And for 4, we have 4, 2, or 0 positive number of positive values of x. And so the number of positive values of I would be 4, 3, 2, 1, or 0. So you can see that there's many different options, or many different possibilities that could happen depending on number of sign changes. So here's an example of the projects with multiple sign changes. So you can see first we have a initial cost of 4 million. Then we have some benefits that represent this linear trend. So they represent arithmetic gradient series. They're being reduced by 1 million. So the A would be 3.5 million, and then the G would be 1 million. And then notice it's still continuous. These series are continuous all the way. So we have another sign change. So this linear trend continues, and the arithmetic gradient actually ends here at 7. So notice that makes two sign changes. One from negative 4 million to the positive, and then here between 4 and 5, from 4 at 4 it was still positive, at 5 becomes negative. So there is a second sign change of cash flows. So if we were to find for different i's, to find the function of present worth or present value of all of these cash flows at different i's, and then plot them as the curve, it gets this curve like this. And notice there's actually two places where it crosses So it has two roots. One root here between 0% and 10%, so maybe somewhere around 7% or something like that. And then another root, or the crossing of level 0, is between 30% and 40%. So here's another root. Here's an example of other type of cash flows. So again, cash flows, let's notice how many sign changes we have here. Here's a negative cash flow, then it becomes positive. So one sign change between 0 and 1, years 0 and 1, then positive all the way through 4, and another sign change between 4 and 5, that's the second sign change, then again a sign change from 5 to 6, from negative to positive, that's the third sign change, and then it remains to be positive. So 3 sign changes. So again, that could lead to multiple roots. However, right, if you look at the present worth, again multiplied by 1,000 and thousands, we'll plot them. This is what the type of curves that we're gonna get. So we can see till 50% we get single root there between 20 and 30, a little after 20, so maybe around 23% or something like that. So now here's another example. We start with negative cash flow, and then it becomes positive. So one sign change here between 0 and 1, from negative to positive, and then again from positive to negative between years 6 and 7. So there's 2, or from year 6 to year 7. So 2 sign changes. Again, plotting this, what we're gonna get is something like this, where you can see that actually there's 2 sign changes, but one of them is negative, the root is negative. So because we know that interest rate is always positive, we would disregard this negative values. Specifically, we would disregard this root that's a negative root. But the positive root we would take into account, so we would have our interest rate between 0 and 20%. So let's talk about modified internal rate of return, also known as MIRR. To get that, we're going to combine cash flows in each period into a single net receipt, RT, or net expense, ET, and find the present worth of the expenses with the financing rate. So this is the equation that we would use to find the present worth of the expenses with the financing rate. And then find the future worth of all the receipts with the investing rate. So notice these are different rates. This E financing, that's our financing rate. This is E investing, this is the investing rate. So again, the costs are moved to the present, and all the benefits are moved to the future. And that is useful, this method is useful in terms of making sure that there's only one sign change. And all the expenses, the negative, will be in the present, all the positive will be in the future, so there's only one single time change. So then we can find the modified, so it's not the internal rate of return, it's modified internal rate of return, which makes the present worth and future worth equivalent. So setting up this equation, we're finding the future value of present worth, for example, f given p at modified internal rate of return over n periods. So present worth of expenses discounted to the future is going to equal to future worth of all the receipts. So again, expenses are negative cash flows, receipts are all positive cash flows. So that guarantees us a single sign change and therefore single root. So if we were to plug in the values from here, right? So this is just a summation. This big sigma sign just denotes the summation for different T's, right? So maybe we start with 0 and would be expenses at time 0, and then again, we don't need to discount it. In that case, it's just the discount factor is just 1. But then for 1, it would be discount factor was T1. For 2, it would be discount was 2. And then all the way to N, it would be here's the expense N would be discounted with a discount factor P given F over N. And the same thing here regarding this sigma T. It's just basically a summation of different products here, of different receipts that are discounted to the future. And so then we are plugging in these summations here, and that gives us a large equation from which to find MIRR. So here's an example of modified internal rate of return calculations. So you already seen this this cash flow diagram. So again, there's two different sign changes, one between period 0 and 1, and another between 4 and 5. So we can apply the modified internal rate of return calculations, and using that, all of the expenses, which this is an expense, and also during 5, 6, and 7 we have expenses, all of the expenses are moved to present. And all of the receipts, which are these blue arrows pointing up, here starting at year 1 all the way through year 4, we're going to combine them all together and move them to the future. So again, this is what we're going to have, right? We're going to combine all of these. Notice when we're combining the 0.5 M, we discount it back to the present. So 0.5 M multiplied by P given F at 8%. That's our investing rate. So this is our this is our financing rate. So financing rate is 8%. We're gonna we might have a different investing rate. So 8% is financing rate. So 8%, we discounting this back at 5 periods. So this is 5. Then 1.5 happens at 6. So we discount it back. So this is a future amount. This we need to find its present value. So P given F, and then at 6 because it happens at 6. And then last but not least, we also add this 2.5 that happens in year 7. So again, discounting it back, finding its present value given the future. So P given F, 8% financing rate over 7 periods because it happens at 7. And altogether, all the sum of values is present worth of all the expenses. And then, as I said, we're going to grab all of these and one by one move them to the future. And so now we did the same for the cash flows. Starting with 3.5, that's going to be 6 moves 6 periods back, not back, forward to 7. So 7 minus 1 is 6, right? So 6 periods. 2.5 is going to be 7 minus 2. That's going to be 5 periods. So 2.5, 5 periods. Again, all of these are present with respect to the period 7, which is a future. So it's going to be find its future worth given the present. So I've given P, and 8% is our also the same as a financing rate. This is an investing rate, so that's investing rate. So now we got all of these, right, including 1.5 also discounted 4 periods back, and 0.5 discounted 3 periods back. In fact, 7 minus 4, because it occurs at 4, is 3. So now we got all of this, and so now we only have one negative cash flow. That's a combination of all the negative cash flows, and one positive cash flow. That's a combination of all the receipts or positive cash flows. And now we can find a modified internal rate of return. So computing these values, this is the present worth of expenses, and this is future worth of receipts. And then, alright, we need to find the modified internal rate of return. We're just gonna set up the following equation. It's gonna be present worth of all the expenses. I don't want that like this. Gonna be future multiplied by the discount factor of find its future value, given that this is a present, at MIRR over n, and n in this case is 7 years. We discounted forward to the future 7 periods, and that's going to be the same as the future worth of these receipts. Okay, don't want this to happen. Alright, so now we got this. We're gonna plug in the values. We plug in the value of present worth of expenses, and that's this value here, which is 6.744 million, 44,000 million. So now that's what we're gonna plug in, 6.744 multiplied by the future given fund future amount given present at MIRR 7, and then here the future value of receipts is this much, so that's what we're going to plug in, 11.898 million. And then we can find the discount factor F given P MIRR 7 is going to be this 11.898 divided by 6.744. So using a calculator, we're going to have this. So the F given P MIRR 7 is going to be 1.764 and then 2 approximately. And then if you go and look in the tables in the book and look for on different pages, we look for different values of interest rate, and then look at the column that says F given P and the row that says 7, we can find that there's actually different values, say maybe 8 and 9%, that would have somewhat close to this values. So then we can plug in, say, MIRR, plug in 7% or 8% and 9%, and then interpolate, and that can lead us to find that MIRR is 8.45%. Okay, so that's how we would find that modified internal rate of return. Modified internal rate of return is 8.45%. Great. So let's take a look at what type of ways we can use spreadsheets to find the modified internal rate of return. There is actually a function in Excel called MIRR, and that function is used to find modified internal rate of return of a series of cash flows and the periods from 0 to n, and it uses finance rate and then reinvestment rate. The finance rate is used for negative cash flows, and reinvestment rate is used for positive cash flows. And the values is a range of values that we use from zero, basically cash flow values, from period 0 all the way through period n. So this is a very, very useful function because it simplifies all the computations. As you see in our example previously, we actually even would have to use interpolation. So all those numerical calculations are done for you in Excel. All right, thanks a lot. This is it, and I hope this additional chapter was very useful for you.